In this lesson, we are going to define electronegativity and discuss how electronegativity affects the properties of a covalent bond in determining whether a bond is polar, nonpolar, or ionic. Electronegativity is the ability of an atom to attract an electron to itself in a covalent bond. We can think about electronegativity as a measure of the selfishness of an atom. When we compare two atoms in a bond, we can look at their different electronegativity, and what we will see is that one of them tends to have a more electronegative value. In that case, the electrons are going to be closer to and spend more time around the more electronegative atom. When we look at the periodic trends, we see that electronegativity increases from left to right and from bottom to top. Note that we do not see the electronegativity values of the transition elements. Our focus is primarily on our main group elements, which are the first two and the last 6 columns. Also notice that the noble gases on the far right side of the periodic table do not have electronegativity values. Remember that electronegativity is the attraction for an electron in a covalent bond. And since noble gases do not form covalent bonds, we don't look at their electronegativity values. To determine the specific element and its electronegativity value, compare this to a periodic table. For example, we see helium at the upper right and fluorine, which has an electronegativity value of 4, and this is the highest electronegativity value of the elements on the periodic table. Hydrogen is on the far left. Remember, it is a nonmetal even though it's on the left side of the periodic table and has electronegativity of 2.1. We also see oxygen, nitrogen, and carbon. You do not need to memorize specific values for electronegativities. You should know the periodic trends and know that fluorine is the highest. Polarity results from the uneven sharing of electrons. This can occur in a bond or in a molecule. We're going to start by looking at a bond where we can compare two different electronegativity values. For example, the bond between H and F. When we look at this, what we see is that fluorine has a partial negative because we're not transferring electrons like we do in ionic compounds where we would transfer so you get a complete negative charge, and we don't associate a specific value with this. We just know that because fluorine is more electronegative, it's going to have more electron density around it from the bond. So it has a partial negative. The hydrogen with the lower electronegativity value will have a partial positive value. And what we see is that the electrons are going to be shared unevenly between these two atoms. And we would call this a polar bond. As with many things in chemistry, there is a spectrum of polarity, starting from no difference in electronegativity, such as when two atoms are the same, to something where we have a very large difference in electronegativity, such as between a metal and a nonmetal. And in fact, when it's a very high value, what we see is that it forms an ionic compound. As with many things, there is no specific cutoff where we change from nonpolar to polar to ionic, because there are other properties which help determine the features of a bond. However, these cutoffs can be used as a reference point. Although there are exceptions, we're going to use these rules to classify our bonds. A nonpolar compound will have a difference in electronegativity between 0 and 0.4. A polar bond will have a difference in electronegativity greater than 0.4 and less than or equal to 1.7, and an ionic bond will have a difference in electronegativity greater than 1.7. We will use the cutoffs of 0.4 meaning nonpolar and 1.7 as polar. Let's look at some examples to classify bonds as nonpolar, polar, or ionic. We'll start with silicon and phosphorus. The first thing we need to do is locate the electronegativity values for these two elements on the periodic table. Notice that phosphorus has an electronegativity of 2.1 and silicon of 1.8. The difference in electronegativity is 0.3, therefore we have a nonpolar bond. In order to determine that this is nonpolar, you would need the specific values given in the table of electronegativity values. However, not all problems need this information, and you should be able to solve problems with and without the specific values. There are examples in the end of chapter exercises that let you practice the two different types of problems you can solve with and without the table of values. Our next example is HH bond. Because it's the same atom, it obviously has the same electronegativity value, so it has a difference of 0, making it a non-polar bond. Next, we have carbon and oxygen. We're going to locate the electronegativity values for carbon and oxygen on our table, and we find that carbon has a value of 2.5 and oxygen has a value of 3.5. The difference in electronegativity is 1, therefore we have a polar bond. For NaCl, we have a value of 0.9 and 3.0, so we get a difference of 2.1, which tells us we have an ionic bond, and this is consistent with what we learned previously, that a metal and a nonmetal will form an ionic bond. Without specific values, use the trends and assume that different elements have different electronegativity values. One relationship that you should know is between carbon and hydrogen. The difference in electronegativity is 0.4 and a CH bond is nonpolar. You don't need to know the specific values, but you should know that the CH bond is nonpolar.